Aren't we all hoping for a greener future? It is well known that the pharma industry is the most waste producers, where through traditional organic synthetic processes, so much waste are introduced to the environment, making it really sick. Today we will talk about how we can improve drug synthesis through an alternative process, which is where biocatalysis comes along. With biocatalysis, pharmaceutical processes are shorter, produce less waste, and reduce manufacturing costs and environmental impacts. But what is biocatalysis? The use of biocatalyzed processes is increasingly becoming recognized as a very important part inside green chemistry. This is because those synthetic crafts are mediated by enzymes to speed up chemical reactions, which are natural substances from biological sources or whole cells. They are a promise for a greener future because they are generally conducted under mild reaction conditions at ambient temperature and can use water as a reaction medium in many cases, reducing waste, energy consumption, as well as eliminating the use of solvents that can be highly toxic and persistent in the environment. It is well established that the preparation of chiral molecules have been challenging in the pharmaceutical industry, which led us to discover the use of biocatalysis as an alternative, due to the high chemo and enantioselectiveness commonly displaced by enzymes. In addition to the increasingly strict rules for safety, quality, and environmentally friendly approaches for industrial synthetic processes, in which biocatalysis offers more sustainable, healthy, and economically attractive strategies for the synthesis of chiralbiologically active compounds that satisfy most of the 12 principles of green chemistry. In the case of ibuprofen, enantioselectiveness is important to select for anti-inflammatory effect, which is displaced by the S-enantiomer. We need this friend whenever we catch a cold, have a stomach ache, a headache, but wouldn't you actually feel better when you know that a greener approach can be used for its preparation? As ibuprofen belongs to the family of 2-arylpropenic acids, they're considered the most important family of non-steroidal anti-inflammatory drugs that act by inhibiting cyclooxygenase 2, reducing the production of inflammation-mediating prostaglandins. Despite the progress in asymmetric synthesis, the resolution of phrasemates was still the strategy of choice in the preparation of chiroprofens, because it was challenging to obtain a pure enantiomer form. However, this is where biocatalysis is presented as an attractive and greener alternative.
This biocatalytic process involves the use of lipases as catalysts for the resolution of profens. The resolution of the ibuprofen S enantiomer employs lipase from the yeast Candida cylindricea to catalyze the enantioselective hydrolysis of racemic ibuprofen methoxyethyl ester, which shows enantio preference towards the S enantiomer. This process is performed within enzymatic membrane reactors where the lipases are immobilized within the pores of a hollow fiber membrane. The membrane allows the use of a biphasic system in which reaction and separation occur simultaneously. The hydrophobic substrate is delivered in the organic phase and chiral ibuprofen is extracted by the aqueous phase into the lumen of the hollow fibers. Another membrane module, adjusted to a higher pH, is then combined to separate the product. This system allows for the resolution of ibuprofen on a multi-kilogram scale, with optically pure products obtained with an enantiomeric excess of 96%, which is very pure. This reaction has optimal operating conditions of 40-degree temperatures and a pH of 8, and has an E factor of 13. E factor is a green chemistry metric that is used to highlight the mass of waste produced per mass of product. A 13 is very good, as the traditional industrial synthetic approaches of the pharmaceutical industry, which favors the use of solvents at extremely high temperatures, have E factors from anywhere from 25 to 100, indicating how much greener an approach biocatalysis is. Carrier-free immobilization techniques have also been applied in the production of chiral ibuprofen. These techniques involve the systemic alteration of reaction conditions and have become useful ways to optimize reactions and increase the robustness of biocatalysts. Enzyme immobilization is probably one of the most traditionally studied and used methods, as it increases enzyme stability, helping to enable enzyme employment in different solvents, pH and temperature extremes, and exceptionally high substrate concentrations.
So in summary, what makes biocatalysis in the context of S-ibuprofen preparation green? The synthesis of many pharmaceuticals is known to involve a large array of hazardous substances, e.g., when ibuprofen was first patented, the initial 6-step synthesis involved aluminium chloride, corrosive, and sodium ethoxide, corrosive and flammable. On an industrial scale, the handling and disposal of these chemicals can be difficult to do so in a manner which is not harmful to the environment. This process was not only an environmental hazard, but produced ibuprofen as a racemate mixture. This is not ideal as the S-enantiomer is the most effective. The first revised green synthesis, the BHC method, used neither of the above-mentioned chemicals, instead using hydrofluoric acid as a catalyst. However, hydrofluoric acid, while not consumed in the reaction process, is nonetheless corrosive and acutely toxic. In contrast, lipase catalyzed enantiomer-selective hydrolysis of ibuprofen, methoxyethyl ester, is a better and greener alternative. Lipase, just like the majority of biocatalysts, is less hazardous and biodegradable. The type of solvent used in a biocatalyzed reaction is crucial for the sustainability of the process. In this case, water was the choice of solvent. Generally, water represents undoubtedly the second best choice after neat conditions. It is also known that water can accelerate reaction rate through hydrophobic effects, particularly in organic synthesis. Biocatalysts can enable water to act as a very efficient solvent in organic reactions, as one of the great advantages of biotransformations is the inherent enzyme ability to work in aqueous media. The feasibility of using water and ionic liquids as solvents is further increased through the use of membranes, e.g., as mentioned before, in preparation of S-ibuprofen, a hollow fiber membrane with a mobilized Candida cylindricae lipase can be used. Employing this membrane is very beneficial as it allows the synthesis and separation of reactions to occur simultaneously due to the solubility differences of the reactants and the products. The improvements in atom economy and selectivity displayed by lipase-catalyzed enantiomer-selective hydrolysis of ibuprofen are applications of green chemistry principles, as catalysts were used to minimize energy consumption, the choice of reaction conditions minimize environmental persistence and risk of toxicity, biodegradability of lipase, and efficiency of reaction allowed to maximize materials incorporation into the final product. This enabled the production of a better product with minimal amount of waste using a more environmentally friendly approach. Hence, biocatalysis was a good choice for a greener approach.